They're sitting here on the desktop when you need them. Your two files are sitting here, right here, when you need them.
Thank you.
And Floor has the first talk, right? So.
Yes.
She mic'd up. Let's get her mic'd up.
Yes. Yeah, I feel like also.
Hey folks, we'll get started for the afternoon. So our first speaker of the afternoon session will be changing gears again. No more exoplanets. I get to learn about something new today. Our first speaker will be Flora Brokarden from CFA, telling us about gravitational wave paleontology.
All right, and if there's actually one thing I hope you remember from this talk, is that actually massive stars are kind of the dinosaurs of our universe. And I'll explain you why. And I'll talk a bit about the role of these next generation telescopes like HabWorlds, about how to probe the formation, lives, and deaths of these massive stars. And especially with application to what I call gravitational wave paleontology, which is that we can use the fossils of massive stars, namely black holes, to understand how these stars, once upon a time, far away from us lived, which I think is very exciting. I'm going to try to give a bit of a broader introduction, since it's probably not the field that most of you are experts in. And feel free to ask any questions, especially basic ones, because I'm sure I'm going to use a lot of jargon and forget to explain things at the end of the talk. Okay, but first, see if this will progress. I see. All right, I guess this works. Yeah, so compared to our sun shown here, massive stars are these stars that are 10 to 200 times the size of our sun. I hope this at some point work. I can. I'm just going to try this.
You might just try the.
Okay. The clicker, yeah. It's okay. Okay, all right. So these stars are very special. They live fast and die young. They have lifetimes about 1,000 times as short as our sun. And they're also very rare. The IMF tells us, initial mass function tells us that only 1 in 1,000 stars is actually born as a massive star. And so this is why, currently, it's super challenging to observe a statistical population of massive stars and study them in detail, because they're so difficult to find. And this is both true for our own Milky Way, where we often depend on super expensive surveys, like large surveys with the Hubble Space Telescope, as well as like in more distant environments, like other galaxies further away from us, where it basically becomes impossible to study individual stars. And so because of this, there's very little things that we know about massive stars, but there's one thing we do know about them. And this is that they play a pivotal role in shaping our universe. So they, for instance, trigger and trace star formation. Their massive winds produce a lot of feedback. They cause these transients like supernova and often outshine star-forming galaxies. They might be super important for the reionization of our universe. And when these stars die, they create these black holes and neutron stars. But maybe most interesting is they actually produce and are responsible for the production of all oxygen that we breathe here on Earth. And there's one really cool thing about these stars, and that's that they often live in pairs or even higher multiples. And these stars, when they are in a pair, they actually can drastically alter their evolution. They can interact and exchange mass. And these massive stars, when they die, they go supernovae. Now, I don't have the same budget as Interstellar, but what can happen is that they form two black holes, which I here visualize as almost the same. And so only if they can stay together as stars, which actually most of them don't do, they get disrupted, they can form a pair of black holes. And these black holes over billions of years can spiral and eventually collide, forming a slightly more massive black hole. Now, this is important because in 2015, something special happened. For the first time, astronomers detected such a collision of two black holes. And this raised the question or the opportunity to many astronomers like me, can we use these observations of merging black holes as a kind of paleontology to understand and learn about how these stars formed, lived, and died in the past? And so this, again, is this new emerging field that I call gravitational wave paleontology, studying the lives of stars using their fossils as black holes that we see today. Okay, so as a quick reminder, how does this work, gravitational waves? Well, all around us, there is these pairs of black holes that occasionally collide, during which they produce these gravitational waves, waves in space-time itself, that travel through space and can eventually reach us here on Earth. Now, this is a bit exaggerated, but it basically causes ripples, and the Earth and everyone itself to squeeze and stretch a little bit over time, which we can pick up with these gravitational wave detectors. But it's super, super tiny. This signal is actually smaller than the size of an atom. You wouldn't notice it in your daily life. But from these signals, which are shown here, these chirps, scientists can actually unravel properties of the black holes, such as their masses, mass ratios, and even their spins. And this is the sound that actually you would hear if you translate this frequency to sound, which I think is so cool. There's one thing that's super, super special about these stellar mass black hole collisions, and that's that they actually probe stars over cosmic times. And to explain this, this is a picture of our universe where basically you have the Big Bang, first formation of stars, and then to the far right is where we are. And there's something interesting. So if you look at how these pairs form, is that a pair of stars actually forms a pair of black holes in just a few million years, which is nothing in the lifetime of the universe. But then these black holes actually take many billions and billions of years before they eventually collide. And so this means that the black holes that are colliding, even the ones that we're seeing today locally, already probe the formation and lives of massive stars like deep down in our universe. Now, of course, they don't travel through space like this, but they're in a galaxy that like evolves over time. So this is a bit image. And okay, so if we go back to this picture, it's like, this would be great, right? We can use these black hole collisions to finally study these massive stars. But there's one problem. And that is similar to how maybe fossils don't immediately tell you whether a dinosaur had feathers, these black hole collisions don't immediately have an imprint of the stars themselves. And so in practice, what we need to do is we need to forward model these stars to basically model how they would form and live, and then compare that to the observations that we see today. And so in practice, we do this with these kind of like stellar evolution models, which most simply put is like you put in two hypothetical stars, like a pair of stars, and then this model includes like stellar evolution, stellar winds, like all the processes that these stars can go through, and then in the end determines, based on, for instance, hypothetical masses of the stars, whether it forms a black hole, like this one. Pretty cool. Okay, so you might think, end of talk, this is great. We have this, we can evolve stars, like people have lots of different simulations that can do this stellar evolution. So we're ready for this field. Well, the main conclusion that I hope to also give to you is that actually this arrow of like how do these stars evolve and how do we model this has 5 key challenges that is currently limiting us from doing this. And this is what I call the so-called gravitational wave paleontology uncertainty challenge. And so there's 5 barriers that is keeping us from being completely able to do this. Okay, so what are these? Well, quickly. The first one is that actually we're not that certain about how these gravitational wave sources form. And here are some of the different channels that have been proposed. And as you know, there's many theorists, and when theorists see observations, they like to come up with lots of different ways that these can form. So to give an example, this first one is a theory that says, oh, maybe these black holes actually come from isolated pairs of stars. So you basically start with a very wide binary that is not connected to like any other star dynamically, so just an isolated binary. And then this binary evolves over time. The initially more massive star expands first, enabling mass transfer episode to the other stars. The other star can accrete. At the end of this mass transfer, this star is stripped. And now you have this stripped star, like helium star, in a pair with another star. Eventually, this star goes supernova and can, for instance, leave behind the first compact object, a black hole. Now, eventually, the other star will also expand. Maybe there's an X-ray binary phase. And in this case, when it expands its envelope, the mass transfer might actually be unstable. So this is a so-called common envelope phase, where basically the compact object is engulfed in the envelope of the star, and due to drag, spirals in. And eventually, if the envelope can be ejected, you might end up with this very close binary that consists of a black hole and another stripped helium star that maybe is visible as like a Wolf-Rayet star. The other star also goes supernova, and you form your second compact object, a neutron star or a black hole. And eventually, these stars or these compact objects can collide and form the graph. Okay, so this is one channel. But as I said, there's actually many, many more channels. So they might actually form from these very first stars in the universe. So maybe the gravitational waves today are actually probing population 3 stars, the very metaphor stars. They might come from triples or multiple order systems. They might have formed chemically homogeneous evolution, so that there's a lot of mixing and rapidly rotating stars that mix all their hydrogen from the core to the envelope. Or there's this whole other type of channels where it's like, maybe they actually form in these dynamical environments. So for instance, in globular cluster or young open star clusters, where instead of just living in a pair, they can have all these like 3 body interactions. Eventually kick one out. This is my COVID activity. And what you basically end up with is always like a closer black hole pair that can then spiral in the age of the universe. Okay, so this is our first challenge. And so in practice, what we need to do is when we evolve these stars, we don't just have to evolve it for one type of formation channel, but like rerun our simulations, including all these different formation channels and different formation pathways of forming these black holes. The second challenge is that we're actually not so sure about the initial conditions. Things like how many stars are actually in binaries, like the multiplicity. What is their metallicity? What is their initial rotation or initial environment? And this is actually really, really important. It can drastically change your simulation outcome because it's been shown that actually the metallicities of the star drastically changes, for instance, what the black holes are, like what the properties of the black holes are that collide. So for instance, here you see the total mass of the black hole pair that's colliding as a function of metallicity. And you can see that it drastically changes from kind of like forming 20 solar mass black holes to like a total of 80 solar mass black holes in the collision. And so in practice, again, we don't need to just simulate over those two properties, but all these different axes and initial conditions, which are uncertain. And so we have to rerun our simulations again with all these different initial conditions. The third challenge and barrier is that actually these mergers are a very rare outcome of stellar evolution, both in our simulations and in the real world. So often it happens that I need to simulate 1,000 massive star pairs before one of them turns into a gravitational wave source. Because actually most of these stars, even though they start out of pairs, like typically break up during their lives. Maybe just like relationships of real celebrities on Earth. And so what this leads to is that if you have too few sources in your simulation, you get a lot of Poisson noise just from undersampling. And so again, we need to really run more simulations to find enough data points and resolve this issue. Okay, now come the real barriers. Because another thing is that actually this stellar evolution is very, very uncertain. I showed you this evolutionary path, but it includes all these different phases like mass transfer, supernova explosions that we don't know so well. And so in practice, we add free parameters or knobs that we can tune to try out different physics. Like we use parameterized prescriptions, tune the knobs, and then see if this changes our simulation outcome. So again, we need to rerun all our simulations, trying to completely rerun the population, but then include these uncertain physics. And then maybe most importantly is that this stellar evolution, especially for binary physics, is really, really, really uncertain. So this is, for instance, how most stellar evolution codes currently model supernova. It's just a prescription with some free parameters that are here shown as knobs. But of course, in practice, it probably looks more something like this, or this is like a 3D hydro simulation of a supernova that is just orders more messy and probably leads to different results than our simple equations do. So combined, it's really like we need way, way more computational time to include all these uncertainties and overcome all these barriers. And so often when I think about my field, I think like, yeah, in practice, we want to jump over these barriers, but maybe it kind of looks more like this, or feels more like this. We're just trying to like maybe go over some of these barriers, and we're just failing and failing and failing and getting the next one. And so I think it's an honest question that we have to ask, which is, with so many uncertainties, is there like anything we can learn from gravitational waves? And I think the answer is like, yes, we can do this, but we need you. And I think especially we need more observations, and I would say we especially need UV, if anything. And really a lot of people working on UV and like increasing this technology. And I'll explain you why. Like because I think the biggest things that we need to resolve some of these issues will come from UV observations of massive stars. So let me give you a few examples in the last 10 minutes. Okay, so I spoke about these like uncertain initial conditions. So it becomes really, really important that we start constraining initial conditions of stars, as this is one of the key uncertainties that's currently producing one of these barriers in our simulations. And so these future telescopes like HabWorlds are actually super, super exciting because they will do a couple of things. So they might actually constrain stellar multiplicity and system properties, and especially those of wide binaries, which I think is very exciting because we think those wide binaries are the ones that make these gravitational wave sources. And those wide binaries are like inaccessible with most other like telescopes that don't have the same width. At the same time, I think there will be some talks tomorrow. The telescope will also constrain the initial mass function in different environments and also help us understand very massive stars. And these very massive stars, these are stars above like 150 solar masses that we know exist. They might actually be one of the key sources of gravitational waves. But very little is known about them, and you need the UV to really identify them from the spectra. And here's, for instance, an example in this figure on the right, where you just see that these proposed telescopes, so this is from LUVAR, can find some of these sources, and in this case, like detect like the main sequence turnout of stellar populations, and then detect things like age and masses to much further distances than like current telescopes. And so this becomes really important to understand like how initial mass function, but also properties of stars behave as you go to different environments and galaxies further away from us. It will also help us constrain the properties of star clusters and like resolve more stars in star clusters and star clusters further away from us, and help us constrain the properties of globular clusters, which is what we think might be the key source of these dynamical gravitational wave formations. And maybe even find some of these intermediate mass black holes, or find evidence for intermediate mass black holes, which will also tell us a lot about how these stellar mass black holes form and whether they form these bigger black holes. And in general, constrain a lot about star formation histories. But again, you need this high angular resolution that these telescopes provide, and especially also the UV resolution that will really help us identify these massive stars where the lines are often dominated in the UV spectrum to identify them. Okay, I think the second most interesting case for UV that will really, really help us and help us reduce one of the biggest uncertainties is to better understand stellar evolution physics, but especially looking at strip stars. So I showed you this image, and there's two special phases. So these strip stars are the stars here, these pink stars, that are basically stripped from their envelope. And we think every gravitational wave source that has formed has gone through such a phase. But the challenge is that these are some of the most uncertain phases in stellar evolution. Like Wolf-Rayet stars, we don't know much about their winds, we don't know much about their evolution, like what their sizes are, etc. And so it's really, really important that we get more observations of these stripped helium stars. Now, interestingly, a few have recently been found. These were found as black hole imposters. So maybe you've heard about this like 70 solar mass black hole, LB1, that was like residing in our galaxy, or the nearest by a black hole that then later on there was like a black hole detective, Karim al-Badri, and like others, were shown to be actually stripped helium stars. So these are stars that can hide as black holes in the stellar spectra because they basically are much dimmer than a star that isn't stripped. And so you might not see it and thereby think it's a compact object, but it's actually a stripped helium star. And so there's, for instance, work by Ylva Goldberg that showed that these helium stars, like the key way to find them is actually to look in the UV, where they outshine their companions. So in the optical, much higher, usually the companion stars, so these are helium, main sequence star, like outshines and dominates the light. But once you go to UV region, you can actually pick up these stars. And at least a decent fraction of them might outshine their companion in UV. And so actually very recently, as of last week, there was a paper published where they, by doing this, found the first 25 of these intermediate helium strip stars. And so I think this is great news for us because these are one of the key observations that will help us like improve our models and like constrain physics. And the fact that there's now 25 is really good. It means these targets are out there. We just need to like build better UV telescopes and do more UV observations to find them and like observe their properties. And in addition, I want to emphasize that actually UV lines are also super, super powerful tracers and will help with like understanding stellar winds, and especially these helium star winds that are so, so important. They're one of the key uncertainties right now in this whole gravitational wave paleontology. Then last, I also wanted to emphasize that UV and these type of HabWorlds observations are really, really important to also understand supernova, one of the other biggest uncertainties in our models. And I wanted to give an example with this recently found nearby supernovae in the Pinwheel Galaxy. And one of the interesting things is that the UV behaves very differently compared to the optical spectra in these supernovae. And especially if you're interested in the early supernova light curves, UV is very important because it peaks usually early, and it has several spectral line features like iron groups that are really, really helpful in identifying the elements of these supernova. And it's super, super interesting because these early phases tell us a lot about the actual physics that's launching the supernova and the stellar winds that were there before like the full supernova went off. And this is also the case for kilonova, where UV becomes really, really important because it's actually the key way to detect many of the R process, so heavy elements in those spectra. And again, like in this type of kilonovas, the UV is really important for understanding the early behavior of these kilonova detections. Okay, so that's a lot. It's a lot of UV, and actually tomorrow there's a couple of more talks about like how to look at star formation at like massive stars. So I'm sure there will be more people talking about the importance of like habitable worlds for massive stars in general. But I wanted to end with kind of this picture, which is Habitable Worlds is going to be launched in hopefully 2035 or 2040. And that's actually a very, very exciting timeline. It gives us enough time to, you know, like prepare ourselves to be ready to like understand and get most out of the data. But most interestingly, it actually coincides with when the next generation gravitational wave detectors will be launched. So this graph just shows you the number of detections, gravitational wave detections that we've seen now and that we will see in the future. So currently we're in 04 and we have seen about like 100 events in the past 3 runs. Then there's some future 05 and Voyager, but we're actually mostly excited about this Cosmic Explorer and Einstein Telescope era, where in 2035, hopefully, we'll build this new detector that's like basically 10 times larger than the current detectors. And because gravitational wave actually scales as 1 over distance, but not as 1 over distance squared in amplitude, you can go much, much deeper. And so we're actually going to go to an era where we started, you know, with 100 detections today to millions of detections per year. And one of the exciting things is that this is not only just a huge number of detections, but it would also mean that if we can do this gravitational wave paleontology, that it basically comes down with a $1 billion cost to about $100 per star to study stars, which I think is like the cheapest way to study stars. Like, this is a great observatory. So I would like to say it's not a gravitational wave observatory, maybe it's a massive star observatory. But most excitingly, it will actually detect these gravitational waves much further. So currently, LIGO and Virgo and Kagra, they can see kind of stellar mass black holes between 10 and 100 solar masses up to redshift 1, which is already pretty far. But these next generation detectors, they're actually going to detect things out to and beyond redshift 20 and easily redshift 100, which means for the nearby sources, you're going to have insane SNRs, like hundreds of thousands of SNR. And excitingly, if you don't understand what this means, like it's actually going to detect every single merging black hole in the entire universe. We don't have to worry about selection functions, biases. This will be a complete survey of every single stellar mass black hole that's colliding in the universe. It will see it if it's out there, which I just think is truly amazing. And we're going to combine this with, of course, many, many other interesting facilities. Like there will be more gravitational wave detectors like LISA and the SKA, IPTA, that are going to detect other gravitational wave sources, such as like double white dwarfs, galaxies, AGNs. And most excitingly, of course, as you've seen in many other of the talks, there's going to be a whole range of telescopes that will help us like further make most of all this information and data. And so I truly hope that like with these telescopes like Habitable Worlds, we can kind of go away from this left picture where we're just running into barriers to kind of like understanding and constraining some of these uncertainties to go to this right picture. And I'll just end with that. I hope that we can do this so that we can start doing gravitational wave paleontology and using all these gravitational wave observations to study stars that will then help us understand these massive stars and hopefully contribute, you know, both through gravitational waves, but also many, many other surveys. It's just one example to all these different fields and open questions that we have concerning massive stars. Thank you.
Thank you, Flora, for a great talk. I'll start with questions in the room. Introduce yourself for the folks online,
Sure.
if you don't mind.
Thank you. That was excellent. Thank you. I'm Evgenia Shkolnik from ASU. So what is the typical, say, NUV, FUV magnitude of these stripped helium stars?
Oh, I don't know that by heart, but I can look that up and come back to you based
so
on
where
like
did
the ones that they
observations
found.
come from? The spectra of the 25 came from HST?
No, from
Swift?
Swift, yeah, Swift, yeah.
Okay.
Yeah.
Okay.
So it's pretty good. Yeah, it's more that they were like hidden. It's like hard to understand, like it was previously hard to understand like how to identify them rather than they're impossible to find. It was actually this open question of like, where are they? They should be out there, but yeah.
Great talk. So I'm Claudia Scarlata from the University of Minnesota, and I have a question regarding what are the best galaxies that you would use to study these massive stars, given that you said the pairs form in the distant universe.
Yeah, that's a good question. We think a lot of, especially the black holes that collide, might form from lower metallicity environments. So really galaxies that have a lot of star formation, or at least at the point that the stars form that then form the black holes, like have metallicities of like below a fifth solar. So this is why basically LMC and SMC are too high metallicity. I think especially those properties of like low metallicity, extremely low metallicity galaxies would be very helpful. But then, unfortunately, but also fortunately, like they come from a mixture of galaxies. So it's still an open question, like depending on a combination of their delay times and this, like how well is each metallicity, like how well are they informing these sources? That combination will like decide which galaxies they actually reside. So this is still a big open question. Yeah. And I will say actually one of the open questions that we have is that often galaxy observers look at like metallicity, but in like oxygen, whereas we're actually interested in metallicity in more like iron lines. Because the iron drives the stellar winds that we want to understand and that really drastically alter the evolution of stars. So even that translation, figuring that out is super important for us.
I think we have a question online.
We have a question from Nasir. How long does it take you to record and collect data?
Oh, for the gravitational waves?
I think so.
Yeah. I mean, currently they detect them like on the spot. So I get a text message every other day or so that there's like a new gravitational wave source. But then it takes, of course, at the moment it still takes like kind of a year or 2 years before the data is released and is publicly available with like the parameter estimations of like what are the masses, just because they want to do a thorough study of like what's the noise during the instrument run and take that into account. But I think the plan is starting 05 that actually most data and source properties will be like released immediately, like probably within a day or so. Yeah.
I think we'll take one more question from the room and then move on to our next speaker.
Okay. Hi, Rachel Somerville from CCA Flatiron. So one of the things you mentioned that I thought was really interesting was the possibility of constraining the stellar IMF, and in particular constraining it as it was in the past.
Yeah.
So what do you think the prospects are for being able to do that in a meaningful way? Do we have to wait until Cosmic Explorer, or can we do that maybe a little bit sooner?
Oh, that's a good question. I think we definitely need more data to like untangle some of these parameters or better understand some of like how metallicity impacts or masses impact, like the initial masses or properties impact the evolution. But I think that will probably still take 10 years. So it will end up being the same time scale as when these detectors come online. So
Thank you.
yeah.
Let's thank Florian. And our next speaker will be Rebecca Larson from RIT.
Okay, sure. I don't have a pocket for this, but yeah.
Your batteries are dead.
No problem. Hi, everyone. My name is Rebecca Larson. I am a postdoc at RIT as of a few months ago. And so I'm excited to be here today and to kind of advocate for the galaxy science that we can do with the Habitable Worlds Observatory. And since a lot of you are perhaps not experts in my field, as I've learned a lot from you all, I thought I would start with talking about where we came from prior to where we are right now with JWST and where we could go in the future, including with the Habitable Worlds Observatory. And so every, talk about the early universe has their favorite graph of how the universe evolved. And so over cosmic history, we've gone through several different phases. In this particular graphic, we have the early universe and the Big Bang on the right-hand side, and then today on the left. And so as we go further back in redshift space, or further back in time, we're looking at a different kind of universe. And we're trying to understand, how did galaxies grow and evolve and form into the ones that we see now, and how do we study this? And where we've been, you know, with ground-based telescopes is here we're increasing redshift to the right, or looking further and further back into the early universe to the right-hand side. And so we've continued to advance and to see further and further back into the early universe and understand these earlier galaxies and the universe itself. And I like to use this graphic, even though it's a little bit out of date, because it used to say future with JWST, and now I get to just slap a nice big current sticker on top of it, because this is actually actively happening. We've increased, you know, how far back in time we can look, the more distant galaxies that we can study and understand how they formed and evolved, and really put into context this evolution of galaxies over time. And so just to take a step back and understand, how do we do that? How do we find distant galaxies? And most of the ways we do this is with images, where we have, in this case, this is a great video that I like to share, where at the top we're showing the Hubble imaging filters. And how we find galaxies is that as we increase in redshift, the galaxies themselves, the light gets redshifted, and so they actually drop out of our UV filters. And so for a UV telescope, I would like to also advocate for thinking about how far we can go into the infrared. To 1 to 2 microns, I think, would be great for us to also include, because in the UV, we don't see any of these distant galaxies. They just aren't there. And so because of this phenomenon, this is actually how we find the distant galaxies, is where do we lose their light? In the shorter wavelengths. And so this is how we find these galaxies, and what we did with Hubble. Here we have ACS and with C3 images, and you might be like, that's a cute bunch of pixels. What are you doing? And so, right, and then Spitzer, bless his heart, did a really good job of, you know, getting us into the farther infrared data where we really needed to have this information to study these galaxies. And so where we were was looking for these dropout galaxies, these few pixel smudges, and trying to understand this galaxy itself is, you know, 500 million years after the Big Bang, and this is how we were finding them. And trying to characterize them, obviously you would like to use spectroscopy to do so, because you get more information than just from imaging. But, you know, before JWST again, you know, this is the rest frame UV and optical emission from a galaxy. This is the model spectrum here. And if you were to observe a galaxy at redshift 7.5 billion years after the Big Bang, this is where the observed wavelengths of those lights would be. You're already past a micron for the far, like the UV light that we see from these sources. There's nothing detected lower, you know, at shorter wavelengths than this. And I think we have a lot of really interesting science that we could do from the ground using these 6 to 10 meter class telescopes, but already we're in the infrared. And we needed the best and the, you know, brightest things for us to be able to study them from the grounds of the atmosphere. And prior to JWST, these wavelengths here, this rest optical light from these galaxies, or even in the UV, was just completely unreachable. We didn't have any kind of detectors or ability to see this. And so we still tried, still worked very hard for many years to try to see this Lyman alpha emission, these galaxies, put them in context of, you know, the universe that they lived in was different. There was neutral hydrogen, and it blocked all of this UV emission and this optical, this ultraviolet light from these galaxies. The reason we don't see it is because all of the neutral hydrogen in between the galaxies themselves was actually eating up all of this light. And so if we could see this Lyman alpha emission, this really bright emission from star-forming galaxies, then we could say that perhaps these galaxies themselves existed in an ionized region, that there's something that happened and changed the nature of this. This is an open question as to like what reionized the universe, what were the sources of this ionizing radiation, and what galaxies can we actually see in, you know, Lyman alpha, because at the time that was the only line that we could detect. We only had, you know, the ability to see this left portion of the spectrum. We didn't have any detectors to study any of these other emission lines that weren't affected by this, you know, neutral hydrogen. And so we can say something about the universe as well as the galaxies when we're able to study them. And this is some data that we have from Keck prior to, again, JWST. And this was where we were. We had the Hubble, like the ultra deep field, and, you know, for a lot of hours, Hubble stared, you know, for thousands of hours at one place, and we, you know, thousands of galaxies in here. And this is what we were able to do when we spent a lot of time on this telescope to look further and further back. And how did we do? Well, I think we did a good job. We did as best as we could. And previously, one of those Lyman alpha emission lines I showed you was this previous record holder at redshift 8.68, where we found a Lyman alpha emission line. That was from Keck, and then Hubble found GNZ11. And I would like for you to just kind of maybe remember this graphic as to how far back we've been able to go and what we've been able to study and what they looked like in our Hubble data. They're very small and quite faint, even though these two are some of the brightest things that we had detected. And so a big effort prior to having the technology, we really needed to see this time in the universe's history, these early galaxies, and to understand them. We have that technological capability now. So where did we come from? Well, pain and a lot of effort and trying to do something in a very difficult way because that's all the technology we had. And so when we're talking about the future of telescopes and what do we need now, what do we need to build to answer these questions, it's a really fun time to be talking about my specific field because we just went through this. We just went through this complete revolution in our understanding of the early universe because we got a new telescope, a new observatory that had capabilities we didn't have before. So with JWST, not only are we getting, longer wavelength coverage, but we're getting higher resolution. And so what we're able to do here is just a bit of a comparison for you to kind of show, this is one of those images I showed you at the beginning where we had the little smudges in Hubble here on the left, and then trying to keep it as, like actually accurate where those wavelengths are that we're detecting these images. Spitzer on the far right there. And in fact, some of the first images that came through from JWST, we are still covering the same wavelengths as some of Hubble, but you might notice that we have a much higher, detection. The sensitivity is much better for JWST than it was for Hubble, even at the same wavelengths that they operate at. And then we also fill in all those gaps. We also have these detections that we just didn't have before, this wavelength coverage we didn't have. And especially in the far infrared. So again, Spitzer, no hate to Spitzer. It was amazing for the things that it did for us. But the sensitivity that we have with JWST is significantly better, and the resolution is significantly better. And these are the data we had and the data we have now. And so we're already making huge gains in our technological abilities and scientific capabilities because of the new observatory. And so I just kind of also want to highlight a few things that we've done with this. And so, for example, these clusters, which we've seen lots of really pretty pictures of, I also want to point out that these early distant galaxies, like I showed before, are just tiny little smudges in Hubble. And so you can see in this left panel here, the little images are the actual images from Hubble. And it's just kind of a few pixels, about 5. Very happy little pixels that are a galaxy. And that's what we had. This is the information we had, and we measured the distance in the redshift. And when JWST came online and we got images, the increase in the resolution shows us it's actually 2. It's a merging system of galaxies. We would have never known there's actually 2 things here. So on the far right, this is the JWST images. And we were correct at the distance, but we didn't know the details. And now we're starting to see the details, and we're starting to understand maybe why these are the bright things that we're seeing. Maybe the merger is kicking off a lot of star formation, and this is putting things into context we didn't have. One of the early programs that I'm part of is the Sears Survey, and I think every time I give a talk, I have to update what we pointed at because things keep getting changed and moved around due to shorts and all this other stuff. The most current version we have of our program and all the data has been taken. And I just want to show some fun eye candy because these images are incredible. We are getting an amazing amount of data, but in 1 hour of observations per filter and in 7 filters here. This is not a deep field with JWST. This is a survey field and a test case scenario, and the data is exquisite. It's incredible, and the things that we're learning are amazing, and there's so many galaxies, and I really do encourage, especially people who maybe aren't trying to work on the data, to go enjoy it in the visual capacity that it is. And so we do have these high resolution images for you to just kind of appreciate the scale of what we're starting to study. And in fact, last Thursday, timely talk, we had our full survey image, and it is actually available to be downloaded. So it was the press release that came out on Thursday that included the full survey field. So this is just near cam, right? So these are wavelengths that Hubble did kind of cover, and then a little bit longer than that, but at resolutions and sensitivities we didn't have before. One of the first things that we found, surprisingly, was Maisie's galaxy. It was a galaxy at redshift about 12. We thought we were going to need many, many, many more hours with JWST to see things this far. We thought we'd be super lucky to see something at redshift like 11. Or 12 would have been great, but like we didn't think we would be able to see further than that with the data. But the sensitivity of the telescope was so great that we actually had a lot more galaxies that we're seeing in the early universe. It was surprising because of the ability of this telescope to see these things with the sensitivity and the resolution to kind of resolve them. We also had situations where we were confused because sometimes a galaxy can be lower redshift and closer by and dusty, and it looks like a high redshift galaxy that's just further away. And so these are two examples of sources where we had two competing photometric redshifts. We have these models that we try to understand of the early universe galaxies are fundamentally different. And we talked previously a little bit about Metallicity and how we measure these things. We assume certain things about the early universe and those galaxies, and unless we're using the correct models, unless we're understanding these galaxies would be different than the ones that we would be looking at today, we can't necessarily distinguish, and sometimes we just have emission lines that we need to detect. And so like I showed before, the wavelength coverage that we had prior to JWST was just this end here on the blue. But this entire spectrum we can see with JWST now. We have the wavelength coverage to see this entire portion of a galaxy at, this is just an example at redshift 7.5. So if you remember what I said before, the previous record holder from Keck was a redshift 8.68 galaxy, and that's great, records are fun. But what's interesting about it is that we only had this one tiny emission line from Lyman alpha, and having the wavelength coverage and the sensitivity to actually see the rest of the spectrum, I cried when I saw this because we've tried for forever to try to see this Lyman alpha emission. I'm drawing a box, and that's about as sensitive as Keck was, and that's the only wavelengths that we were able to see for these sources. The only thing we knew about galaxies in the early universe and could characterize, aside from ALMA, this is in the north, couldn't see it with ALMA, but we were not able to study this portion of the spectrum of these sources. And with, 1 hour with JWST, one of the brightest sources that we knew about, we have an incredible amount of information that we're learning. And GNC11, the previous record holder, this is a little bit more than 1 hour, but it's incredible. It's incredible the information that we now have. We had nothing but maybe a break in the spectrum, but now we actually see, not only do we see the continuum, the break in the spectrum, we see emission lines. We can understand things about this source we couldn't do before. And I want to just continue to keep your attention here on this 1 to 2 micron region, where we still have a lot of information, a lot of science that we could be doing, and we don't understand a lot of things about this particular source or about any of these other high redshift ones, even in these wavelength range, in the UV of these galaxies, even though we're seeing it at the 1 to 2 micron range. Daisies galaxy, the one we discovered, we got spectra of it and confirmed it's actually at 11.4. Again, we're seeing this continuum, and again, at 1.5 microns, at redshift 11, you're able to actually detect these sources with JWST and not in a lot of exposure time. We answered the question as to whether those galaxies were high redshift or low redshift, and we also found more. We are able to do a lot of really cool science and understanding galaxies at all kinds of different redshifts because we have this technology. I'm just going to highlight a bunch of results really fast, because to talk about where we are now, it has been a year with JWST, and I genuinely can't fit everything we've learned about early galaxies in this talk. And I want to talk about where we can go. And so I want to highlight Jades. Jades has done an incredible job of getting deep spectra, deep imaging, and discovering galaxies in the 10 to 13 redshift range, and then also confirming them with spectra. Iger has used the GRISM, so slitless spectroscopy has been an incredibly powerful tool for studying and characterizing galaxies. For the first time, we're able to really build up statistical samples of galaxies in the early universe. Prior to JWST, we had about 10 that were above redshift 8, and we all just kind of knew what they were. And now I don't know how to make a database of galaxies. We've never had this many that we've needed to do it. These are problems that, I'm not upset about having, but are things that I'm a little upset about having to do. But, right, these are things that we're learning that we're just completely bombarded by the amount of information we now have for galaxies. We have an IFU on NearSpec that's able to do detailed, spectra, pixel by pixel analysis of galaxies. And in this case, this is a redshift 4 galaxy that we can see. This is from the templates team here. And we're actually being able to measure the metallicity in galaxies, the gradients, how the stars are forming in different parts of these galaxies in detail. These are instruments and technologies that we didn't have. And we're also able to understand the properties of these galaxies. We want to know what reionized the universe. Well, now we can measure how much of the ionizing radiation escapes these galaxies. This is something that's a really big, still open question, but we can't necessarily do it if we don't have the sensitivity to do so. And we're seeing some of the brightest things, and of course the first things that we looked at were the ones we knew about, and those were the brightest sources. We're learning a lot about black holes in the early universe. And so how did we get these really bright quasars that we've observed here on the right-hand side? These are incredibly bright, massive, active black holes in the early universe that we didn't understand how they could get that big that fast. And we just genuinely had no observations at redshifts higher than this of active black holes. So we have theory, and we're starting now to populate this. This is one of the first ones that we've found and actually been able to measure black hole mass for it. For the first time, we're getting data here. This is a completely unknown, untested, time in the history of the universe, which is something that we can study because of this telescope. We're working on the next generation of deep fields. We've seen the Hubble deep field, but we're getting the depths in a fraction of the time that we needed with Hubble because of the increase in sensitivity. This is NG deep. The papers are out now, and I don't have fun animations or videos that I can't juggle, but I really want you to look at the pretty pictures because this data, again, this is only half of our total exposure time. This is half of what we were trying to do for deep field because of technical difficulties, but we're able to still do some incredible science because this is just an incredibly higher resolution and highly sensitive telescope. And we also have programs like Cosmos Web that are covering a large area. I'm doing a slight disservice to this program because we have things coming out that I want you to be hype about and I don't want to give away. But this is just our first data. And if you kind of look at the top left there, it's just a small fraction of the entire field. And we have about half of it now. And if you think that those other pictures, which was 1 pointing or 10 pointings, this is insane. The data and the amount of area that we're covering in the galaxies we can recover is crazy because we have, the ability to do this in a relatively quick exposure time. We can cover a larger area at a depth that's, necessary for us to do science without spending tens of thousands of hours, trying to build up these fields because of the increase in sensitivity. And as a Galaxy person, obviously I'm going to show you a lot of Galaxy teams. The Pearls team also has a time domain field. So what we're building up is, yes, a deep field, but we're doing it in this case over time. This is enabling supernova science and all kinds of other transient science with JWST because we are observing something that's a continuous viewing zone. Over time, we're enabling a lot of other fields of astronomy to use the same data to do also additionally cool science. So I want to stress, this is where we are right now, as of honestly 2 months ago, because it's too fast. Everything is moving really fast. And, this is what we're learning. And where are we going to go? And with Habitable Worlds, we're going to be there in a bit. And there's a few things coming down the pipeline prior to this happening. So what's next? Roman is happening. This is where we're going. And if the field of view of Hubble and being able to see things at this resolution, we can, with JWST, we're having effectively like the same kind of field of view. And this is just a fun picture I like to show because with Roman, we would see the entire blue shape all at once. One image would be this big. So while we can study galaxies in detail right now with JWST, we have the sensitivity. Now we're going to have a field of view that's going to cover a larger area. So we can do a lot more about cosmic variance and overcoming all of the, perhaps differences and put, again, in context, statistical understanding of galaxies. And if we see something, is it weird or is it normal? And we don't know when we only have a handful. The next generation of ground telescopes, the ELTs, these are things that are also going to be coming online. And for example, the Giant Magellan Telescope is under construction and we'll see first light before the Habitable Worlds will. And this is just a simulation from the CODA 2 simulation showing time is increasing. And then this is space in the Y direction. So it's a trip to look at. But what you're seeing is like this is reionization. So neutral hydrogen to ionized hydrogen. And for the field of view, we can be lucky and point, Hubble or JWST or Keck or something at what we hope is an ionized region of the universe because we can search for that. And at the bottom here, I'm showing the field of view of JWST and Keck. But the field of view of something like, some of the proposed GMT instruments is massive. So we would be able to, again, see and not necessarily always have to just be lucky in pointing it, but we're overcoming this variance here. And so the field of view that we're going to gain from the telescopes that are coming up is a massive increase in the field of view, and we have the sensitivity and all these other stuff. You might be saying to yourself, that's great. Why do you need our telescope? You guys are doing so good. Like, you have all of this stuff now, and I feel you because we have a lot of stuff. And it's a great time to be a galaxy person because we got the observatory we've been needing for so long. And so what is there left to do? We're going to get these other ones. They're going to do a lot of great science. We're going to increase our field of view. We'll be able to look at more of the sky and understand it in the same kind of detail. And so here I'm showing kind of where we are now again. And so here this is, wavelength, on the left-hand side, we're increasing in wavelength. So again, I understand we're not going to get into the infrared necessarily with Habitable Worlds, and that's great. And JWST, as you can see, is doing a great job. The sensitivity, the magnitude that we're able to achieve in only 10,000 seconds. This is a 10 sigma depth too, right? I mean, half of the things we study with Hubble, like 5 sigma, if we were lucky, right? So 10 sigma, I mean, this is being quite generous. These are the depths that we're able to achieve. So as you can already see, HST did a great job, and JWST's sensitivity is a lot better. So these are the reasons why we're seeing some of this with JWST that we just couldn't see with Hubble. So our actual size of our telescope matters for our resolution and our sensitivity, and where would we find the ELTs would be doing a great job. But with Habitable Worlds, we're covering a wavelength range at a depth that's insane in all of the best ways, right? I mean, if you assume an 8-meter telescope with a 6.5-meter inscribed diameter, right, so akin to LUVOIR B is where I think a lot of these calculations are coming from. And here on the right-hand side, it's the time to reach a signal-to-noise of 10. So you could get down to 30th magnitude in 10 hours with the Habitable Worlds Observatory, which is something that is impossible without years of observations with any of these other telescopes. And so already you're able to see the fainter things. And what does that do for us? Well, we can also go deeper too. If you actually spend time doing a deep field with the Habitable Worlds Observatory, you're going to be able to detect things as small as the LMC at redshift 7. These are things that will be possible with the sensitivity of a telescope like this. And while I agree, we have a lot of great science we're able to do with the telescopes we have and that we are going to have, this is, again, still unprecedented advancements in our ability to see early things in the universe. We've seen this before, and I'm going to kind of go over it a bit because Rachel talked about it earlier, but this is, the luminosity function of galaxies in the early universe and how we're able to see the depth, given the depth we have in sensitivities, and we don't know if this turns over. Are there fewer, galaxies at these, lower, actual fainter magnitudes at higher redshift? We don't know. We don't have the sensitivity, but we'd be able to do that with something, again, like LUVOIR A, which in a perfect world, we'd all have giant telescopes that we could do whatever we want with, but, maybe even with, an 8-meter telescope or as big as you want to make it, it'd be great. But, all of these things are possible, and the science would still not be possible without something like the Habitable Worlds Observatory. And again, we talk about the resolution. We didn't know that some of these systems were multiple galaxies merging together. We only had 5 pixels with HST, and now we have 2 blurry little blobs, but the ability to resolve these things in 1 week of observations with something like an 8-meter telescope with Habitable Worlds is even better than a month of observations with ELTs, right? These are things that we would be able to do that we couldn't do even with the telescopes that are coming up. And so I would encourage us to think about including, like 1 micron observations. We could study even the UV of these high redshift galaxies in the early universe, and also see the fainter things that we would not be able to see even with what we have now. I just want to say a brief acknowledgement to all of the people who have made all these telescopes possible, and I also want to encourage us in the planning of future observatories to consider the impact that our science cases have on the people who will be doing the work. I know that there's a lot of early career scientists that have been doing a lot of work to make JWST possible, and it has truly revolutionized my field and many others. And I think that we need to be good stewards of the work that they put in and the effort they put in, and giving them the credit for the work that they do, and building a better community for the future of these observatories looking forward. And I think that that's something that should be just as important to talk about as the science is. With that, I was thinking.
Very much for a great talk and an interesting comment there at the end. Some good food for thought. Take questions from the room.
Anastasia Space Telescope, how do you determine the redshift levels when you have like 5 pixels?
Yeah, so it is a bit difficult to understand if it's, maybe some kind of, we check for persistence, if there's something bright that was observed before. We have to check other wavelengths as well. So it's not just looking in the Hubble images, we're also checking if we can in radio data and all this other to kind of put this all together. And if we only have a few pixels, we can say, again, we have really deep data from the ground. We have images there, and we combine all of the information from all of the telescopes. It can't just be, and even with JWST, it's not just JWST data. We're using data from all of the telescopes. It really, truly is like a combined effort and building on what we have now and what we're using and what we will have to like make sure that we're answering like the full picture. We're looking at the whole wavelength spectrum and filling in the gaps for what we don't have, where we only have a few pixels. And I think, it's not easy to do, and I wouldn't recommend it if you have a different career path. But, it's something that we are able to do because we include a lot of other information at different wavelengths from different telescopes as well.
Right. Gabriel Giono, Space Research Institute in Austria. Just a question for my understanding. You showed a graph where you expect the HWO to have better sensitivity than James Webb in the infrared. Can you explain why is it? And is there a technology breakthrough that are expected to? Yeah, this one.
Mm-hmm. So JWST is 6-meter telescope, right? And we have cameras and technologies that were developed a couple years ago. And so right? And so I think it's a decision about optics, it's about upgradability, and it's also about, learning and new cameras and CCDs that are better and the way that it's being, built. And this is coming based off of some of the LUVOIR, plans. And so I think it's an increase in our technological capability just as much as it is as a larger telescope. Because HabWorlds at, 8 meters would actually be bigger than JWST.
Time for one more question in the room, if we have one. Sure.
Great talk. I just wanted to follow up on that. Was obviously the major question for the infrared is the telescope temperature, because it drives the background. But you're only asking to go into the near infrared, a portion of the ways, and then so the question really is, what temperature would it need to be to actually make an improvement over what JWST can do with today's technology or yesterday's technology? And so it'd be great if, I don't know if you've done any simulations or others have, to look at how that actually varies as a function of temperature, because understanding that breakpoint would be really, really valuable.
Yes, I believe that's part of some of the, the LUVOIR calculations and things like that. I don't have that information off the top of my head for you, but that is also something really important to think about. And I think, if we need to cool it, it's going to be out at L2. We're already, a bit further away. And so perhaps that helps us a little bit. And maybe part of the serviceable mission is sending more coolant out there, or maybe again, like HST had with C3 upgrade. These are things that we could do for a mission that is designed to be upgradable. And maybe one of those things is to figure out how to put an instrument out there that could stay cool enough to go longer wavelengths.
Thank you very much. For our final talk in this session, we'll hear again on a new topic from Thaisa Sorshi-Berman about AGN and galaxy evolution through time. Get to turn it back.
Oh, there you go.
Well, I think it's not fair that I speak after Rebecca because she has all the new results on AGN back to the beginning of the universe. But I'm going to talk about my research in nearby AGN. So galaxy evolution and AGN. Okay, space bar. Okay. So a little bit of motivation, then I'm going to talk about AGN feeding, AGN feedback, more distant AGN as observed with JWST, other projects, and what we can do with habitable worlds. Okay, so we all know this relation that indicates there is coevolution between AGN and galaxies, the relation between the mass of the black hole and the bulge mass. Another relation that shows coevolution of black holes and galaxies is that the fact that the black hole accretion rate that occurs in AGN along cosmic history is proportional to the star formation rate along cosmic history. So AGN are important for galaxy evolution. And so in order to understand this coevolution, we have to look for two aspects. And one is the AGN feeding. And in this review, we discussed the processes of AGN feeding on different scales from 10 kiloparsecs or even larger extragalactic scales down to the inner parsec. And I'm going to talk about two of these scales, the extragalactic scales, and talk about a recent study that we have done using SDSS images of a sample of QSO2s nearby, smaller than 0.2, and about 400 QSO2s, and we paired it with a control sample of non-active galaxies. And we found that most QSO2s present signatures of mergers. So the AGN is connected to mergers, is produced by mergers on large scales. And if I understood correctly what Rebecca said, that, when you look this very far away galaxies, you always also see mergers. So I think that, it's important to look for mergers over the whole history of the universe. Maybe they are the cause of the AGN. They are triggering AGN. So to look at the more distant universe, we have these imaging surveys, like the Roman telescope, the LSST at Rubin telescope. So the image you'll say if we see these pairs of galaxies or mergers. But if we want to probe the effect of the interactions, we need to map the star formation, map inflows, outflows, and gas excitation. And for this, we need integral field spectroscopy. I also would like to talk about inflows or AGN feeding on 100 parsec scales. So this work began with this imaging survey where early type AGN, as compared to nearby control galaxies, we saw an excess of dusty structure within the inner 100 parsecs. Okay, and so this suggests that these dusty structures are channels to feed the supermassive black hole. Models also support this, but to look for if this is tracing the feeding of the supermassive black hole in AGN, we need integral field spectroscopy, and this is what we have done with a group of students and collaborators in this, our group called it AGNIFS, AGN Integral Field Spectroscopy. And so to show an example of what we have done, this is in an spectrum in the K-band. So we did integral field spectroscopy, and each spectrum, we measured the emission lines usually bracket gamma. Here I'm focusing in the molecular hydrogen at 2.12 microns. And we got also the stellar contribution, stellar population and stellar kinematics from these CO bands in the K band. So what we have been finding, what we have found, is that usually the stars show rotation. And for example, the H2, sometimes the bracket gamma also, they also show rotation, but it's distinct from the stellar movement. They show rotation plus inflows. So we usually find blue shifts in the far side, red shifts in the near side that indicate inflows to the center. And in a sample of 36 BAT AGN nearby, we found these inflows in about 50% of them. And we found also inflows in spirals, nuclear spirals, 100 parsec scales, also in the optical in a few sources. Okay. And then we also used these data cubes in the near infrared. In half of the sample, we could perform stellar population synthesis from the spectra, stellar spectra. And the results are these gradients, average gradients that we found for different ages of the stellar population, 50 mega years, 100 to 200, 500 to 700, etc. Hot dust also. So this would be gradients of the stellar population contribution to 2.12 to 2.11 microns. And so what we concluded is that the inner 100 parsecs, when you sample the inner 100 parsecs, you have the stellar population is dominated by intermediate ages, ages between 500 to 2000 mega years, with a mean age 1.5 giga years. So the scenario that it can be concluded is that you have, when you have the feeding of the AGN, there is gas that goes towards the center. First triggers star formation within the inner 100 parsecs or so. And then the gas go inwards and trigger the AGN later. Okay, so there is a delay between the star formation and the triggering of the AGN. And there are similar results that also support this result of the excess of intermediate age stars in the vicinity of AGN. And so, so this shows that it's important to probe these 100 parsec scales if you want to see the gas falling into the black hole, if you want to see the stars, young stars that are related to the presence of AGN. Okay, and so as far as I understood, you know, in the design of the Habitable Worlds Observatory, in principle, you can resolve few hundred parsecs from until the end of the universe. Okay, so I think we can do this. We can look for these structures as a function of distance in the universe. And then another mechanism for coevolution is the AGN feedback. So it's also known that galaxy evolution models cannot reproduce the observation of the galaxy luminosity function if it doesn't consider the effect of AGN feedback. So we need to include AGN feedback to avoid building too large galaxies, forming two large galaxies in the universe that are not observed. And this is just a movie. Let's see if it goes. To illustrate by Travis Fisher, to illustrate how the AGN feedback would work in the nearby universe. This is Markarian 573. So when you have the nuclear activity trigger, you have radiation from the accretion disk, and you have sometimes outflow also from the accretion disk, and this radiation can drive outflows up to 2.5 kiloparsecs. So in the inner few kiloparsecs, there is outflows that you observe in AGN, but the radiation still ionizes gas in the galaxy. So the radiation go farther away. Okay. So one example of study of feedback is this a sample of 8 QSO2s that we observed with HST. This is a continuum image showing the star distribution, and this is the gas distribution. So this is the ionized gas that is imaged in O3. The previous one is the stellar component in the continuum. So we can see that the ionized gas goes much farther away than the continuum. Indicating, and we studied the excitation of this ionized gas, and the gas is matter bounded, and it's obvious that there is radiation escaping into the intergalactic medium, so the AGN can be a source of also ionization of the intergalactic medium. Okay, we did also integral field spectroscopy, and we found very complex profiles, emission line profiles, and we made an assumption that the broadest ones, that is blue shifted, is tracing the outflow. And so we used this broadest component to trace the outflow, and we also found that the outflow goes until 4 kiloparsec, but there is ionized gas emission extending up to 20 kiloparsec. We have also studied outflows with NIFs, and we could find outflows in the molecular hydrogen and in bracket gamma. In molecular hydrogen in 60% of the sample, and in bracket gamma 80% of the sample. And we did several other studies looking for inflows and outflows, and the outflows is summarized here. So we did several studies of outflows, and here what we show is the power of the outflow in ionized gas. So if we put, well, I'll keep running. If we put, these are models for models of feedback, and these are the required level of power to make the outflow to have an impact, a large impact in the galaxy, and a shut down star formation, and to explain the models, the models in order to produce shutting or quenching of star formation, they need this power as a function of the bolometric luminosity of the AGN. So what we are finding with our studies is that the power is a little bit low, okay? So these are many studies that we have done, and the power is below what is necessary to quench star formation in the galaxy. So how we can understand that the power of the outflows that we are getting are below the necessary to quench star formation. Okay? So one explanation is that the AGN feedback is multi-phase. So we need to look not only at the ionized gas, but also at the molecular gas and so far. And so this has been done in several studies. And we have a project at JWST also. The data is taken, it's being reduced to look for a few nearby AGN. We are searching for outflows in the warm molecular gas. So what happens with the molecular gas we can observe the cold molecular gas with ALMA, but the outflows are obtained in CO. So CO is a tracer of the molecular gas H2. In this project, we are going to be able to see the proper molecule in the warm molecular gas H2 directly. This is something that we did also with ALMA, and we did find some cold molecular gas outflows. So this is observations with ALMA of a nearby Cipher galaxy, and this is the ionized gas emission, like a cone leaving the plane of the galaxy. This is gas, molecular gas, rotating the plane. And this is, the green is molecular gas that is not in the plane, that is outflowing. So we do see outflowing molecular gas surrounding the ionized gas in this source. But another explanation also is that the feedback power is stronger, should be stronger at cosmic noon. Because, you know, we have this history of we know that the universe was more active at Z about between 2 and 3, that is cosmic noon. So there are some ground-based studies, like the Super Survey with Symphony, that indicate more powerful outflows at these redshifts. But the geometry and the kinematics is not so well constrained. And then we have this result with JWST by Villezalec et al. Compared to a ground-based study. So this was done with NIPS, the same source observed with NIPS. We just found a blob of gas emission in O3, the ionized gas O3. And some kinematics here, blue shifts and red shifts. But then when we look at that, when they look at with the James Webb, with near spec, you see a much more or less the same scale. You see much more emission, and you see much more kinematics. So we see blue shift is here, zero velocity, red shift. So it's a much more complex picture. So IFU. This is near spec IFU, and they found many things that we did not see in the ground-based study: bipolar outflow, several interacting companions, and because of these companions, the hypothesis that this is the central galaxy of a protocluster. So AGN in the distant universe could be like traces of structure formation. So the case for habitable worlds, as I understand, you know, we could do with more sensitivity this same type of study for high redshift objects. Okay, so I think that although I think that, you know, although we are learning a lot with JWST, we can have more sensitivity with the habitable worlds and do the same studies for even more distant AGN. And then I think Rebecca mentioned this already. So these galaxies in the distant universe, if we can use integral field spectroscopy with the habitable worlds, we can do similar studies as we do in the near universe for these distant galaxies. So we can understand the role of AGN from the present day back to the early universe. And there are these new instruments like LSST, the PFS at Subaru Telescope, Prime Focus Spectrograph Project Survey. So LSST will need follow-up spectroscopy because it's just imaging. And it would be great if you can use like the Habitable Worlds Observatory to follow up on those discoveries. And also in the case of the PFS survey, this is going to be a multi-object spectrograph that observes 1.3 field of view with 2,400 fibers at the same time. We are estimating that we are going to get more than 300,000 galaxies until cosmic noon. And then we can explore the AGN and host galaxy connections on this sample of galaxies. If you could have the Habitable Worlds Observatory, I wanted to mean here integral field spectroscopy. So, so my message here is that the AGN impact galaxy evolution since the early universe. And then to gauge the impact, we have to map the gas flows and the stellar population of the host galaxies over the history of the universe, and ideally 100 parsec scales that we can obtain with the Habitable Worlds Observatory. And I got this from the LUVOIR report in honor of Jason. So I think this is very important also for AGN. We have gas flows also from the cosmic web. And it's important then in the UV, look for these absorptions. And I think it would be great also if you could have the extent, the geometry, and the kinematics of these flows, as also mentioned by Chris Hook this morning. So it's a case of resolved spectroscopy in the UV. Finally, so we can, with the resolution of HWO, we can look for inflows to feed the AGN in beyond local galaxies. So which is the extent, geometry, kinematics, and mass inflow rate. We can also map the stellar population beyond the local galaxy, also if we have integral field spectroscopy. And we can map the interaction, excitation, and outflows. If we have then integral field spectroscopy in the optical and in the infrared. So I would like to advocate that we consider integral field spectroscopy for the habitable worlds, because we can look at what we have studied in the near universe, the details of inflows and outflows, also in the distant universe, intermediate and distant universe, because of the resolution and sensitivity of the observatory. And thank you very much.
Very much, Stacey. Okay, start with some questions in the room.
Thank you very much for a very exciting talk. So I was wondering, for the AGN, for which you have cold molecular gas from ALMA, warm from JWST or Spitzer, and hot from NIFS or Gemini or anything, what is the fraction of shocked H2 as a function of various AGN properties?
Shocked H2, yeah. We are finding some, in some 50% of the sample that we have studied, they show H2 in outflow. And then in these cases, we find signatures of shocks. And also we selected as a sample to observe with JWST ones that had signature of shocks. And I had just today, my collaborator sent a spectrum showing very broadened lines and with blue wings. So I think we are seeing outflows related to shocks in the H2 line.
Thank you for this very nice talk. Jean-Claude Bourret from Marseille. Is there an interest for you to have some polarimetric capability, especially in the UV?
A what capability?
Polarimetric capability.
Yes.
Polarimetric.
Oh, okay.
Spectropolarimetry.
Yeah, well, I never worked with polarimetry, but, I know that's, it's important for, to see reflected light in accretion disk or whatever. No, I think, but I never worked with polarimetry. No.
Do we have any questions? Okay. Any others in the room? Maybe I can take my moderator's prerogative to ask a basic question as somebody not from this field. Can you speak a little bit more to the spectral resolution that you would need? Is it important to resolve the lines themselves to study inflows and outflows, or is simply the spatial distribution of a detection sufficient?
For the kinematics, we need to resolve 100 kilometers per second. Okay, so we have to work with the wavelength, right? So, well, usually 2000 is okay. Resolution 2000 is okay to get outflows and even inflows. A little bit better to have more like NIFs. We had like 3600 resolution. So it's better to see the details of the inflows. Okay, but outflows, usually you can have a little bit lower resolution. What else you mentioned? Angular resolution also, yeah. So I think that it's very important, the 100 parsec scales. So even in models, the 100 parsec scales are scales that are important to define the processes and, to map the inflows and even the interaction, signature of interaction between galaxies. 100 parsec scales are important. Okay.
Thank you very much, Thaisa, and to all our speakers in this session as we look a little farther away from home for an hour. We have a coffee break and should be back at 4 o'clock.
Thank you.
Probably.